So, dear friends, today we will talk about the conductors and what happens, that is electrostatics of conductors. We have had a talk about conductors which have plenty of free charges which can move under the influence of an applied electric field obtained by a potential difference. Shortly we will come to the domain of what is known as current electricity, which is other than electrostatics, where conductors means good conductors, insulator means bad conductors, very bad conductors, and there is an in-between which is called a semiconductor. We will have occasion to talk about these materials. Of course, there are some materials which are also called superconductors. So when the time comes, we can talk about superconductivity. They are very fascinating things. Okay. Now, conductors have, as is written what? They have mobile charge carriers. They do carry charge, positive or negative. Okay. For example, the free electrons in the case of metals. Free electrons in the case of metals. Free in the sense that if I have a metal block, okay, if I have a metal block, copper or silver or iron or gold, or for that matter some alloys also, okay, and the shape and the size is like this. So within the confines of this volume which comprises the metal, the electrons are free to move. How come? I'll tell you. But they cannot escape from any of these sides unless special efforts are done, which I'll describe in the due course of time. So, now in the atoms we have an outer orbit of electrons, and these electrons, they participate in the chemistry of the materials. Okay, there are exchanges, there are sharings, there are many other things which happens so that the solids are formed. This kind of thing is also present in the case of gases and liquids, liquid form or gas form, that is the fluid form, etc., etc. Now, not all, but some of the outer orbit electrons which are not attached to the atom itself as much as the inner orbit electrons are attached. So, they are able to part from the atoms. And this is also true when I talked about the 600 years BC observation with the case of the amber, which was the yellowish raising obtained from the trees, and which was crafted into the beads and other things with which the women used to decorate themselves. Okay, and the beginning of the electrostatics story begins with that. There also, when I rub something, then Of course, some electrons, they leave the thing which is rubbed and go into the thing which rubs. Rubbed and rubs. Okay, rubbing. So, what happens is that these outer orbit valence electrons, which participate in the process of chemical valence, they part from the atoms. But they are free within the metals, free to move. Okay, random motion, like in the case of the atoms and molecules of the gas, when we talk about kinetic theory of gases, and we have done that. They stay, as I told you, within the confines of the metal, okay, and they sort of keep on singing that famous song, Awara hoon, Awara hoon, Ya gardish mein hoon, Asman ka tara hoon, Awara hoon, Awara hoon. So they are wandering around, okay, like vagabonds, okay, like children in the park. They will be moving always in several directions. Okay. So these electrons, which we call free electrons, they are basically Awara electrons. Okay. They roam around. Okay. And they form a kind of a gas within the confines of the metal. They collide with other electrons, with the ions that are formed by them, with non-ionized atoms, etc. So this motion is random, okay, like in the case of the kinetic theory of gases. Okay. So now if you want to make these, to take out some of these electrons, so actually these electrons are bound to the system by what is known as the binding energy. That may change, that may be different for different metals, conductors, etc. Okay. They are also present in the case of semiconductors, the binding energy. This energy has to be paid. Unless you pay for this, with this amount of energy, you will not get the visa to leave the system. Okay. We'll talk about that. So there are so many kinds of emissions of electrons. One is the field emission by means of electric field. Another is thermally heating it, and there is a thermal emission. Then the famous photoelectric emission, secondary emission, etc., etc. So many kinds of emissions. There we are not supposed to talk right now. But if you like, you can Google and search. So what happens is that the electrons are moving inside this dot. You can say that they will form some kind of an electric current, a localized electric current, may they form it. But the net flow of charges in a particular direction, if we have a conductor, and if you say that will the charges move regularly from this side to this side, the answer is no. And the answer is yes. No, in case there is no potential difference between the two sides. But if there is a potential difference from this side to this side, so they will move. Of course, electrons are negatively charged, so they will move towards the positive side from the negative side. Move, and that word that we use is due to the potential difference, due to an external electric field which is applied there, they will drift. They will drift. Being negatively charged, they will drift against the electric field. I'm taking E cap, direction of the electric field. Okay. Now, the heavy ions which are in the core of the metal, okay, they are big heavy people, and electrons are tiny. So between different atoms, etc., they can always move. But these bulky Humpty Dumpty Saturn, all this Humpty Dumpty is not going to move at all. Okay, so these ions, and these must be positive ions because the electron has been taken off from there, they remain fixed. They don't move. This is the case of the metals. But in the case of electrolytes, like silver chloride, or even in the case of the common salt, which is sodium chloride, okay, there are positive and negative points, and I'm showing this as a positive ion. The positive ions, they drift along the electric field, okay, and the negative ions, they drift opposite to the electric field, okay. So there is the electric field which is forcing them to move this side or that side, drift, okay, slowly and gradually drift, okay. Now, besides the electric field which make them drift, in the case of electrolytes, we have the chemical forces. The chemical forces are also active. I'll just stop there because that part of the chemistry is very interesting, and if I go into it, then I'll have to divert from here. In the electrolytes, the positive ions drift along the electric field and the negative opposite to the electric field, like in the case of electrons. So, from one plate to another plate, there is a drift of ions. Silver will go on one side, chlorine will go on other side, etc. Okay. Now, but the binding energy that I talked to you about, the binding energy which binds it to the metal surface, that varies from a few electron volts to a number of electron volts. It all depends. Even there is an engineering in the case of semiconductors which determines the band gap, and you have the capability to decrease it, to increase it, to manage it, to engineer it, and to doctor it. Doctor is not a good word, engineer is a very good word, even tailor is a very good word. Okay. Now with that intro to you, I will see that what are the features of electrostatics of conductors. So we begin with the red, that electric field is zero inside a conductor, whether the conductor is neutral or charged. Okay, the electric field inside the conductor is equal to zero for various reasons that I am going to tell you shortly. Okay. Number two, it's very interesting that, for example, if there is an electric field, okay, there is an electric field and there is a conductor like this, then at any surface, okay, here or here or here or here or here or here, whatever, there may be several surfaces, particularly if the shape is not so straight and geometric as you can think of. It can be any surface. At the surface, the electrostatic field is normal, that is perpendicular to all ds elements. ds, which is a surface vector, surface area vector. If it is not so, for example, and if the conductor has electrons naturally on the surface, okay, always eager to go out, jump the surface, they are there, what will happen? If the electric field is inclined, rather being straight like this, instead it is inclined. So what will happen? It will have a component in this direction also, or a component in this direction or this direction or this direction which is parallel to the surface. Then what will happen? The electrons or the carriers, they will be influenced by that component of the electric field, and that influence should not be there. So naturally they must have an electric field should always be normal to the surface, at this surface. Right? Now then again, from green we go to red. No excess charge in the static situation in the interior of a conductor. So inside the conductor, there should not be any excess charge. So whatever charge is there, the negative and the positive charges, they together should make it a zero, a zero, a zero, a big zero. Okay. So no excess charge in the static situation on the interior of a conductor. So if there is excess charge on this system, it will stay outside, on the surface. Okay, not inside. Okay, nothing doing umpire surface. Okay, that's not allowed. That's illegal. That's not there. So no excess charge in the static situation in the interior of a conductor. In the static situation. But what if we inject charge from one side? I inject charge from this side and it comes out this side, so that there is a regular current or whatever. Then in that case, excess charge may reside temporarily for some time, and no sooner than this arrangement is removed, there will be no excess charge in the static situation. Conductor. I'll tell you of a very interesting story. Well, it happened with one of my young colleagues. I asked him, look here, the electrons are coming like this, they are drifting like this, so that the current is in the opposite direction. Well, my friend, what happens if I suddenly cut this wire? So he thought and thought, and he thought that if there is a cup and you cut this with a very sharp weapon, then electrons will fall inside this cup. He combined his mental this thing with gravitation. Happens. This happens. This has to happen. Man is always doing certain beautiful silly mistakes, and that was one of it. That can never happen. Don't think it will fall. Okay, so no excess charge in the static situation in the interior of a conductor. Okay friends, I'm repeating things because they are very important. Number 4, you have to bear in mind that the electrostatic potential is constant throughout the volume of a conductor. The value inside is always a constant, does not vary, does not change. Okay? In one situation, the value of the potential may be say V1, in another V2, in another Vn, and these values may differ from each other. But if there is a V1, V1 will be there. For another case V2, V2 will be there. It will not change. No change in the value of the potential, electrostatic potential. Why? Why? Because within the volume of the conductor, the value inside has to be a constant. That constant may be 0. That constant may be positive. That constant may be negative. But no change. Once it is there, no change thereafter. Why? Because E is equal to 0 inside the conductor. Right? And I told you that E is equal to minus dV dr. Okay? So that dV should be equal to, V should be equal to a constant. That's the proper explanation. That the electrostatic potential, capital V, is constant throughout the volume of the conductor. Value inside. Now comes a very interesting thing. Again, the red. And it says that at the surface, at any surface, at any point on the surface where we are talking about, the electric field is equal to sigma upon epsilon naught, where sigma is the surface charge density, you know. Epsilon naught, you know. E cap I am writing here, sometimes it's written also as N cap. It is very simple. I don't need much. I have a surface. Okay? I have a surface. And I can talk about the distance r away from the surface. Okay. And symmetrically I take another surface over here. This surface is like this. Okay? The area is A. The area is A. Okay? And the field, for example, if the surface is like this, all charges will stay on the outside, as I said. Okay? This is also same A, this cross section. Now tell me, how about our friend Mr. Gauss? The Gauss law. The Gauss law says that this is what is contained is sigma into A upon epsilon naught. Okay. This will be equal to how much? E into A. E into A. The electric field is over here. Okay. Has to be perpendicular, like I have said, this, that. Okay. So what happens? That A, this side, right hand surface, the electric field is equal to 0, again inside the conductor. Okay, so electric field will exist only outside the conductor, and then we get the electric field as E equal to sigma upon epsilon naught. Of course, then after that, we give it a direction, etc., 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 etc. Okay. Now, the next very beautiful thing, okay, and that is called electrostatic shielding, where I am going to talk to you about. Electrostatic shielding means if there is a volume, it may have walls, etc., or whatever surface is there. If I put it inside a metal surface, like I am telling you about where I am standing. Where I am standing is a basement in my house, big basement. Where I am standing, where my friend, my son is also standing. Okay. This basement has how many walls? It's kind of a rectangular. So 1, 2, 3, 4, 5 the floor and 6 the. Okay. So normally when you build houses, then improperly or whatever, properly or whatever you call it, some people don't have that. Then you have brick walls on the 4 sides. A brick or any kind of a stone or flooring, okay. But this is concrete with iron, and that is what we call a matrix of iron. Iron ka jal. But dear friends, in my house, the safest place is the basement. Because I have all this floor, double jal of iron, concrete field. All these walls, double jals of iron to withhold the pressure from those sides. Now, this one single jal of iron. It has many other floors, 2 floors more. This is the ceiling. Now, I am protected from severe electrostatic changes. Why? Because there is a layer of metal, and if any changes are taking place outside, I am protected. A certain machine, even all transistors, diodes, etc., they have metallic cappings. Okay, so they are protected from wild electrostatic changes. It's very interesting that when a Soviet Union plane, a jet or something like that, that was shot down by the Japanese. And then the Americans, there are 2 blocks, the communist bloc and the non-communist bloc at that time, 2 superpowers. Nowadays there is only one superpower, and that is the United States of America. At that time, so the Americans rushed to see what are the contents of that equipment. I'll call it equipment. That jet. And they were surprised that these Russians are using tube electronics, which was outdated as long as 1960s. They laughed. But later on they came to the conclusion, because there were some solid state components also, okay, there were some transistors, this, that, But the pentodes, hexodes and other things which were working in that device, and they were shielded, they were given electrostatic shielding. So when they were crossing some good barriers where there was a sudden change in the electrostatic field, then at that time the design of the Americans failed, whereas the design of the Russians, it held the line. So electrostatic shielding, the shielding by means of metals, even aluminum foils can do that. They will protect you from, so they are used in many things. Okay, so electrostatic shielding means that I should have an iron cage where I am standing. That iron cage actually protects us. And you also know that in the lightning, all multi-storied buildings, they have something, some kind of a structure up which allows the lightning to run down to the Mother Earth, where they have a deep well, and there they have some very heavy iron plates. If you are living in a building which is multi-storied, you must check with the manager whether that electrostatic, it's not shielding, it is only a path that is given to the lightning to pass through that. I will close my lecture here and invite you to look at these things. And unless you know, that's why I have been slow also and I have not gone into certain details, but I have gone in many other details. You can Google, you can search, you can find, you can discuss. A discussion about these 6 points with 2 or 3 friends is a necessity for you to understand, because they may not understand something, you may not understand something, then you discuss, and these discussions help us make into a strong person. So next we'll go and do other things, but today I am going to do, and I have done this, and this is very interesting. Anywhere it's sigma upon epsilon naught. Okay. Now suppose I am telling you something very interesting. Look at my face. The whole face, the potential will be the same. Now on my face, I have a nose here, and this is very curvy. So when the curvy nose is there, to maintain the same potential, we will see, and I will do that in the due course of time, that the electrostatic field here will be probably maximum, and the least will be here and here and here and here. So it's just like that. Here there will be electric field because the curvatures are there. And to finish off, I will remind you that the relation between curvature and the radius of curvature is that the product of the two is equal to 1. So radius of curvature is equal to 1 upon curvature, and curvature is equal to 1 upon radius of curvature. So it was good to talk to you today, okay, and see you